The next probability distribution function we're going to look at is the normal distribution. If you recorded the weights of a large number of newborn babies, what shape of distribution would you expect to get? Well, if we had a large enough large number of babies, we would expect a histogram which looks symmetrical about the mean here. And I'm sure you can think of some other examples of the normal distribution in the real world, such as the distribution of IB scores. The normal distribution then is characterized by a bell-shaped curve, that's how we describe this, which is symmetrical about the mean. The mean mode and median are the same, and the x-axis is an asymptote to the curve. That's to say that this continues all the way to plus infinity, and this continues all the way to negative infinity. So if we have a random variable x, which has a normal distribution with mean mu and a standard deviation sigma, this can be written x is normally distributed with a mean of mu and a standard deviation sigma. So this would be the variance because it's squared. There are a family of curves of the normal distribution. So, I mean, there are lots of different places that this could be. But we can see that as the mean changes, the shape of the curve doesn't actually change. So as the mean increases from 5, 10 to 15, all that happens is the curve is translated to the right. The spread doesn't change. Conversely, if we keep the mean the same but change or increase the standard deviation, we can see it affects the shape of the curve or the spread. So as we increase the standard deviation, the curve becomes wider and the data is more spread out. Suppose we have a curve like this, and we're trying to find the probability that x is less than 5. Well, we can do that. We know that the total area under the curve is always the same and equal to 1. So everything under here represents all the possible outcomes, so we know that's going to come to 1. In order to calculate the probability of a particular value, so here less than 5, we can calculate it ourselves, but it's a very complicated formula. So panic not, you're not expected to know or indeed use this formula because we can use a function on our calculator which effectively does that for us. However, it can only do that for us if we are using what's called the standard normal distribution, which is a normal distribution where the mean is 0 and the standard deviation is 1. And this random variable is called called z. So the standard normal distribution is written z is normally distributed with a mean of 0 and a standard deviation of 1. How do we use our calculator to complete this complex calculation? Well, provided we are using the standard normal distribution z, we can use it using the normal cumulative distribution function. So if we have here the standard normal distribution and are asked to find the probability that z lies between -2 and 1, we're going to go to probability, distributions, the normal cumulative distribution function. Our lower bound is -2, our upper bound is 1, our mean is 0, and our standard deviation is 1. Just type that in and that function will calculate the probability that z is between -2 and 1, which is 0.819. If you have a question like this, find the probability that z is less than 1, you need to enter a lower bound. We know it goes on to negative infinity. You just need to enter a really large negative number here, so -9 to the E999. Upper bound is 1, the mean and standard deviation as before, and that gives an answer of 0.841. Similarly, greater than -1.5, you would just do -1.5 as your lower bound. Your upper bound would be a really large number. These two as before. D is fairly straightforward. If we've got a standard normal distribution, then the mean is 0. So the probability that z is less than 0 should intuitively be 50% or 0.5. The modulus is a little bit harder. The easiest way to work this out is if if we are trying to find the probability that the modulus of z is greater than 0.8, that's in effect everything except the probability that the modulus of z is less than 0.8. So you can work that value out using your calculator. The lower bound then is negative 0.8, the upper bound is 0.8, these two as before. So that gives us a value of 0.576, and we want to find the probability that the modulus of z is greater than 0.8, so it's going to be 1 minus this value here, which is 0.424. That's all well and good if you happen to have a normal distribution which is in standard form with the mean of 0 and a standard deviation of 1, but that is not really very representative of real-world data. That's not a problem, however, because we can transform real-world data so that it is in a standard form, and we do that using this formula here. So z equals x minus mu over sigma. Suppose we have a random variable x which is normally distributed with a mean of 10 and a standard deviation of 2. So at the moment we can't put this into our calculator because it is not in the standard normal distribution. Suppose we're asked then to find the probability that x is between 9.1 and 10.3. Well, the first thing we're going to have to do is convert each of these into the standard normal distribution using this variable z. We know it's going to be something like this, but first of all we need to convert each of these x values into z values so that we can use our calculator with the standard normal distribution. So first of all, if we look at our lower bound, it's going to be 9.1 minus 10. So in effect we're shifting the curve to the left here so that the mean is centered around 0. And we're then going to divide by the standard deviation, which is 2, so that we have the same shape as the standard normal distribution. And that gives us negative 0.45. We're going to repeat with the upper value, so subtract the mean, divide by the standard deviation, that gives us 0.05. Now we've got these z values, we can use our calculator. So this is what we started off with, which we can't use in our calculator because it's not normally distributed. That's with the variable x. We've converted that into the standard normal distribution with the variable z. And now it's really straightforward to use our calculator exactly as we did before. We're going to use the normal cumulative distribution between negative 0.5 and 0.15 with the mean of 0 and the standard deviation of 1 that we did previously. And that will give you an answer of 0.233. For the final section on the normal distribution, I'm going to show you how you can actually use your calculator to find the probability for any normal distribution without actually having to transform it. So suppose we have a question like this. Eggs are laid by a chicken and are known to have the mass normally distributed with mean 55 grams and standard deviation of 2.5 grams. What is the probability that an egg weighs more than 59 grams, an egg is smaller than 53 grams, and an egg is between 52 and 54 grams? Now, so far we've looked at the standard normal distribution with a mean of 0 and a standard deviation of 1, and we've looked at how you can transform other distributions such that they can be used with the standard normal deviation by generating z values. Now you can actually use your calculator to calculate probabilities straight from other distributions like this. So we are told up here that it is normally distributed. So we've got a variable here, w, which we can call weight, is normally distributed with a mean of 55 grams and a standard deviation of 2.5. So the probability that an egg weighs more than 59 grams, again we can see it's going to be up here somewhere, so we can get a rough idea of the size of the probability. But to solve it using our calculator, we're going to use the normal cumulative distribution function. So our lower bound, well, we want everything that's going to be more than 59 grams. So our lower bound is 59, and our upper bound, remember this is an asymptote, so it goes on forever. So in theory, it goes to infinity. You can see even here it's very small. So we're just going to put in a very large number here, which is 9e to the 999 to represent infinity. Our mean is 55, and our standard deviation is 2.5, and our calculator can actually just calculate that probability straight away. So 5%, and just that looks about right from our initial estimate. Similarly, an egg is smaller than 53 grams, so that's going to be a bit larger, somewhere around about here. So normal CDF, this time our lower bound is actually going to be negative infinity. So again, we're going to use it negative 9 to the E999 as a proxy for negative infinity. Our upper bound this time is going to be 53, mean of 55, standard deviation of 2.5, and that's going to give us an answer of 0.212. Finally, an egg is between 52 and 54 grams. Well, for this, we're just going to use CDF. Lower is 52, upper is 54, same as before here, and that gives us an answer of 0.230.